Today's continuous glucose monitors, or CGMs, test glucose levels through interstitial fluid just under the skin. But what if we could go straight to the source? A new device in development could be the first of its kind, a CBGM, or continuous blood glucose monitor. Welcome to the show. I'm Justin. I have type 1 diabetes, and on here I talk all things diabetes tech, news, and research. We've got this podcast on Mondays, new videos on Fridays on YouTube, and a ton on social media. And I've got a blog at diabetech.info. Links to everything are in the show notes. Today we're diving into Glucotrack, an implantable sensor designed to measure glucose levels directly from the bloodstream. It's placed just under the skin in a quick surgical procedure, and once in, it's designed to last up to 3 years. I sat down with Paul Good, Glucotrack's CEO, and Mark Tapsack, their Chief Scientific Officer. Both bring deep experience from the CGM and implantable sensor world, including the early days of Dexcom when its sensor was still implantable. In this episode, the three of us unpack how Glucotrack works, how it aims to solve some of the biggest pain points with current CGMs, like accuracy issues during rapid glucose changes, skin irritation, and adhesive problems, and how it could ultimately enhance the performance of automated insulin systems. Let's get into it. Mark, Paul, welcome to the show. It's great to have you here, and I am very excited about this piece of technology. I'm looking forward to kind of learning about it. Before we dive into it, though, let's start with you, Mark. Tell us a little bit about your background and kind of what led you to Glucotrack.
Oh yeah, that's a great segue. So thank you for that question. I'm a very curious person. I like understanding how things work, why they work. And I also like kind of tangible things that I can get my hands on, kind of explore a bit, learn and understand how they work. I have a science background, right? I mean, clearly chemistry, hard science. A lot of my colleagues, they explore things in the realm of you can't touch it or see it. And certainly when I was a chemistry professor, it's very hard to connect to students and to make them understand a particular shaped molecule has a particular function because of its shape. Well, why is that difficult? Because it's hard to pick up. It's hard to turn around in your hand. It's hard to understand what a particular molecule size may be. Biologists, they have it a little easier. If I put a picture of a bunny rabbit and a picture of a wolf in front of you, and I ask you which one is the predator and which one is the prey, usually there's enough familiarity with those two objects, right, where you can pick that out pretty quickly from the size of the teeth and the shape of the mouth that the wolf is going to be the one eating the bunny rabbit. So I gravitated towards material science. With respect to science, with respect to chemistry, material science, tangible objects, things like metals, ceramics, and polymers, that was really my maybe segue into science. And so with my first jobs being at Medtronic and Dexcom, that's really the application then of material science in a pretty interesting area. And that is placing items within the body, right? So all active implantables like a pacemaker or the CBGM that we're talking about today, or passive devices like a knee implant or a hip joint, right? These all have to be constructed out of materials. And obviously we want them to last the lifetime of the person. So, longevity is always a big issue. And we want to talk about that today for sure. I was told by some friends of mine very early on that placing objects within the body is more difficult than putting them in space. It's a difficult environment to operate within. The engineering that goes into just these materials of choice, right, that we use to design these implantables. There's a lot of thought and there's decades worth of research that have gone into it. So that's, I think, where I kind of, I drew my love of science, my love of kind of holding on to tangible things. And now I'm presented with, hey, we can design things to place into people's bodies and improve their lives. That's really the connection.
Yeah. And Paul, I know that you have a similar background when it comes to, you've worked at other diabetes companies, you worked at Dexcom. You actually mentioned that the Dexcom was originally, they were working on it to be an implantable. Tell me a little bit about that work that you come from and how it led you to where you are today at Glucotrack.
Sure. Yeah. So actually, you know, I mean, obviously, glucose sensing has been around a long time, and the advent of the finger sticks being rather commonplace, starting, I would say, more so in the mid to late '80s, and then continuing. But in the earlier days of CGM, with the exception of the technology that Medtronic now has, which was prior to that was MiniMed, prior to that was Eli Lilly. That, with the exception of that technology, in the early days, CGM was all about an implantable CGM, and Dexcom was no different. Their technology spun out of the University of Wisconsin in Madison, and a very good group there, and that led the foundation, for the first implantable continuous glucose sensor, and they were the first to prove that. Again, this research group, that you could sense for up to a year in a canine model, and so Dexcom was born out of that. Mark and I were both there in the early days of Dexcom when it was an implantable device. We think of G7, G6, those types of numbers today. But back in those days, it was actually G1, G2, and G3. So those were the implantables. Yeah, that's how it got started. Now the companies, of course, pivoted. MiniMed did a phenomenal job breaking ground, again, FDA approval in 1999 with the first physician-based CGM system. And Dexcom came with, I think, Dexcom or Abbott, one of the two, came with the first patient-based CGM. But yeah, the pivot to the wearable was, due to timeframes. Just clinical studies took a long time for the implantables. And there was a lot that still wasn't known about CGM at that time either. So here we are, many years later, CGM is the standard of care. CGM is well understood. And so we get to stand on the shoulders of giants. Some of those giants were in the early days of CGM, where it was an implantable. Some of those giants are in the latter days of CGM, where it's well understood as a wearable. And some of those giants are in other technologies that we're leveraging to bring this product to market.
Yeah, I actually got to see in person. I went to Medtronic headquarters in LA, and they have an implantable pump, which was very cool. 200 people are using it today. And then they also had an implantable CGM. I don't believe that I don't know if that CGM was like a blood monitor or interstitial. I'm not sure. I don't remember. That's probably in the video for people listening. They can watch. I'll put it in the show notes. But it was so cool to see that. That was so new to me. And to hear this now, that's kind of like where everyone was looking, is really interesting. And it's great to see that a company like yours is coming back and focused on that, because I could see there potentially being a lot of pros to it, which we'll get into in a second. Before we do, how does a device like this, an implantable continuous blood glucose monitor, how does it relate, or how is it similar to something like a pacemaker, which is pretty routine today, this type of implantable?
Yeah, that's a very good question, because that's exactly what we're trying to leverage, right? As Mark mentioned earlier, trying to sense within the body is challenging, because your body sees it as an invader, and so it wants to push it out. And the toughest place, as Mark has taught me many times, and we learned at Dexcom, is the subcutaneous space, because it is the first barrier, to the rest of your body, to your organs and your vessels and so forth. So it's got to be the most aggressive. So as we look to move inside the body and try to overcome some of the challenges of that some patients have with today's technologies, we thought, well, if we're going to do that, let's overcome and go intravascular. But let's not reinvent the wheel here. And if you look at, as you said, cardiac pacemaker technology, it's been around forever. It's very mature. The materials are mature. The devices are mature, the designs are mature, the techniques are mature, and all we're doing is leveraging a lot of those mature techniques. Now, cardiac pacemaker has a pretty big size device. Ours is dramatically smaller in volume, more like an insertable loop recorder that is used to, patients have implanted about 100,000 a year in the U.S. To monitor their heart rhythms, real time. For a period of years. And then the lead goes in like a cardiac pacemaker lead, but instead of going all the way into the heart and anchoring into the cardiac tissue, it just goes 2 inches or 5 centimeters into the subclavian vein and floats there.
What would you say are some of the current limitations to CGMs today that a device like this would come in and be better at?
I'll talk on the human side. Mark could probably talk a little bit more on the chemistry or the biology side.
Sure.
But on the sort of the use case side is patients have to manage. I like to say that we try to get patients to not have to manage their device, to manage their disease. We want to take that device management out of the equation. So you have a set it and forget it type of a situation, if you will, in terms of device, procedure. So you're not every, 7, 10, 14, 15 days replacing a sensor, not worrying about it warming up or getting wonky the first day or getting wonky the last couple of days. And so all of that management stuff, goes away. Some of those concerns go away. I have a grandson with type 1 diabetes, and I see the shelf that his parents have for all of his supplies at home. All that goes away. All the concerns, can I swim with this? No, I got 3 more days of life on this sensor. So from, a human factor standpoint, a lot of that goes away. From a chemical standpoint, I'll pitch it to Mark. There's some advantages there as well.
Yeah, and before Mark gets started, these things popping in my head as a user is, packing for vacations and all of the stress that comes with that. And then maybe having some failures along that trip and not having enough, ripping a CGM off on a car door frame, which I've done enough times. But, all these little things that you have to deal with. The other day, I had 2 CGM failures in a row. Luckily, I was in a situation where I had a whole backup supply, and there's obviously some issues that those sensors have by not activating. But yeah, these little things, these technical issues that people with diabetes are always going through. I love the idea of a set it and forget it device like this. Mark, tell us about kind of some of those physiological advantages to a device like this that's measuring the blood versus the interstitial fluid that, devices like today do.
Sure. So like Paul mentioned just a moment ago, we want the skin to be a very aggressively immune protection environment, right? I mean, my goodness, if it wasn't so, we'd be dying of paper cuts and, thorn pokes and things like that all the time. So, we've certainly evolved so that is quite literally one of the most protected spaces, protected tissues in the body. And then as we kind of go deeper and deeper, you think of like compartments in the body, right? The blood, the brain, you've probably heard blood-brain barriers, right? The brain clearly is a very protected space. And it turns out the vasculature is as well. It doesn't see a lot of invasions. Things that we would purposefully put in our bodies or things that we might either ingest or breathe in or get exposed to, right? There's barriers for those attackers to get into our bloodstream. So if we go ahead and state that we're going to target the bloodstream as our area within which we're going to measure, boy, that's like the superhighway of analytes within our body. If we're trying to pick up not only glucose, but any other item within our body that might be very important for understanding kind of the metabolism and our metabolic activities, there quite literally isn't anything better than blood, right? You go to the hospital, you go to the ER, you don't quite know what's going on. What do those ER docs do? They draw blood, they send it off to the clinical lab right away. We don't have to necessarily spend the company time, effort, and resources to convince doctors that blood values or items measured within the blood are of importance. They've known that. They've known that, since medicine has been practiced. So that's certainly number one. Then number two, compartmental delays, right? Just understanding, again, whether you're measuring blood glucose that is representative and highly accurate, right, for making some kind of therapeutic decision. Again, for a diabetic, is going to be, man, I'm trying to do some quick calculations. I'm thinking about dosing. I think everyone recognizes that there are delays then when we say ingest glucose and how long that gets out into the outermost parts of our bodies, not only our fingertips for taking a capillary measurement, or even within our skin. And I'm sure people that have worn a number of CGMs and have kind of followed their evolution, we've kind of evolved from, say, different tissues even on the body, the belly, the arm, the back of the arm. Now some people looking at the forearm. Those come with complications from the biology and the compartment diffusion aspect as well. So we're just trying to go to the source.
What we, typically this compartmental delay that Mark mentioned is, it's usually not a problem most of the time when your glucose levels are not changing dramatically. But when they are changing dramatically, like, postprandially or exercise, or, when you're stressed or when you're ill, there can be rapid rates of change. And of course, those changes typically happen in the normal glycemic range. So you're either going to go up to a too high level or go down to a too low level. And we believe that, our experience shows us that, we're going to be significantly quicker, effectively real time, as opposed to having that delay, which, publications have shown can be out to, 15 minutes in rapid rates of change. Even a very recent publication from this year demonstrated that. So, the sooner that we can alert the patient that they're going too high, they may be able to dose sooner, spend more time in range. So as well as going low, they can treat themselves sooner, so they can, with orange juice or what have you, to prevent.
I see that with my devices all the time, that my glucose will rise or fall very quickly in the span of, say, just a few minutes, but my device lags by that 10 to 15 minutes, and I'm starting to feel these highs or lows before I'm notified. And that's just what happens with interstitial fluid. So the idea of getting this data directly from the source, it sounds like a much more helpful thing for potentially catching things faster and being able to treat and not have to feel those lows. This episode is sponsored by Omnipod. As someone with T1D and with an incredibly active lifestyle, it's important for me not to get tied up, especially with tubes on my insulin pump. I love to go swimming, lift weights, and play kickball with friends. And with Omnipod 5, I never have to worry about tubes getting in the way. Plus, not having to disconnect helps me to stay in range during all of my favorite physical activities. That includes sexy time too. See if you're eligible for a 30-day trial by visiting omnipod.com/diabetic. On there, you'll see full safety and risk information and trial terms. That's omnipod.com/diabetic. How could a technology like this impact automated insulin delivery systems? A lot of pumps out there, they talk to these external and in some cases implantable Eversense, but all interstitial fluid CGMs. How could a CBGM be an advantage for these AID systems, or the change the way they work?
Yeah, there's I would say, when you look at those, the conventional systems today, you have, interstitial glucose that's being sensed, so you have a compartmental delay there. And then you have subcutaneous insulin delivery, so you have another compartmental delay there. And so as a result, those stack up. I think, again, these AID systems that are out there today are phenomenal. I am, so happy to see it, out there, because especially going back many years ago in this field, to see that we've evolved to those levels. However, because of those two compartmental delays on either side, there are still certain things that a patient needs to do, even on AID, like announcing a meal, for example, and maybe even in some cases, how many carbs are being ingested and so forth. And so one can talk about it being, closed loop, if you will, but at this point, it's still not completely closed loop. Our hope is, and of course we have to prove this clinically, but our hope is, number one, that we can, by getting rid of one of those compartmental delays, that maybe it could be less interaction needed by the patient, is one. And secondly, if the pump has the information that much sooner, maybe the AID, again, it has to be proven, but maybe the AID can have the patient, increase the patient's time in range, and maybe even do it with less insulin, so that those are the types of things that we would like to prove with our technology.
So there already is an implantable on the market, the Eversense, but with this is a CGM. It's testing interstitial fluid, and a disadvantage. I guess you hear implantable, you're like, great, okay, it's testing interstitial fluid, but it's implanted. Well, you still need to wear an outer device, so it kind of defeats the purpose of wearing of an implantable. there are many advantages to the device, don't get me wrong, but
Mm-hmm.
that is like, a disadvantage of an implantable. Does this device need any external, or is the entire thing, or would the entire thing be internal?
Totally internal, no
Okay.
external needed. I mean, other than the smartphone, right, to
Yeah.
receive the data. So it's
Okay.
Bluetooth from the implant through the body to the smartphone.
Since this is testing the blood, would a device like this be nearly 100% accurate? I'm sure you can't say it's 100% accurate, but the reading is coming from the blood. Like, there's no interstitial fluid in the way. So how does that accuracy change?
I'll give a high level answer and let Mark give the more technical answer because he's smarter than me there. But a high level answer is, and we recently had some data at ATTD, for example, that shows that we did our first in human, completed that short study, and our MARDs as one metric were lower than what's commercially available on the market today. And yet we were still disappointed with where we were because we saw even better in animals, and so we understand where you learn everything with every trial, right? And so we expect it to potentially get even lower. As to why it's not zero, I'll pass that one on to Mark, and he can do some explaining on that one.
Oh my gosh, that's a heavy lift on that. Why it's not zero. So, okay, I'm going to take a stab at this a couple of different ways. First off, Justin, this is, in a way, this is a gigantic can of worms. We were in attendance at the Diabetes Technology Society meeting this past year, and we presented there. Before my presentation, there was an entire scientific session around accuracy. How should we talk about accuracy? By what consistent metrics should we talk about accuracy? What does accuracy mean? Should it be with respect to clinical outcomes, or are we talking like an analytical chemistry accuracy, right? Device to device comparison. So there are a ton of nuances when you get into talking about accuracy. I do kind of joke with our internal team, especially on the preclinical side, when we look at some of our animal data against BGMs, for example, right? So we're, off of an animal, we're taking small blood sticks, but we're handling those samples. We're placing that blood sample. That's a living entity, by the way, right? I mean, well, it's alive and it's metabolizing glucose, and so you get into all of these nuances of sampling, handling, and so we'll see MARDs in a short time period in an animal study of like 2.5%, really low, right? I've never seen a CGM come close to that. And again, I joke with our team, I'm like, we should be calibrating the BGM value off of our device, because I probably trust our device, smoothly sitting in the bloodstream, continuously measuring in that kind of environment, no human error in handling specimens and placing it in vials, handling it, putting it on strips, for example, and having to insert the strip, all of those little nuances. So that said, they're inherent to the device itself as well, how we kind of construct the chemistry. We still do need to generate a signal, right? There's time in doing that when we maybe want to filter that signal with respect to electronics noise, right? So there are these little teeny things that kind of creep in and knock us off of having, say, a zero accuracy or perfect accuracy. I don't know, I guess I would call it 100% accurate, right? It's funny. We go to an MARD and you think of numbers getting smaller and smaller, but that's a deviation from perfect. So anyways, I guess I'm doing a roundabout answer to your question. It's never going to be zero because there are other aspects of the measurement itself, both in the electronics, in the chemistry itself. But say time delays, for example, we can design in time delays that are on the order of seconds rather than minutes, but they do exist.
Explain to us what Glucotrack looks like.
Okay, so the electronics, the device is housed in a titanium housing. Again, designed just like an implantable loop recorder. It's actually using a battery from an existing commercial implantable loop recorder for cardiac monitoring, that is. And so the length of that device, about 2/3 of that length is actually battery to give us our 3-year longevity. And then Out of that remaining 1/3, half of that is electronics, and then the other half, which is the clear plastic part at one side of the device, that is where we connect the lead. So if you think of that whole device, that's effectively like if you think of like the G6 as an example, you had this sensor carrier and you had this plug-in electronics transmitter thing. It's kind of like that, right? And then the lead is kind of like that little sensor filament that comes out of the sensor, or and it has wires that go down. It connects into the device. As wires go down to electrodes. It's constructed very similar to a cardiac pacemaker lead, and then there's chemistry placed on it. And I'll pass that over to Mark.
Like Paul mentioned, again, I'm going to start from the materials aspect. We're really trying to de-risk as much of this system as possible, right? So picking lead diameters, and I even use the term lead rather than just sensor because that's a familiar term to interventional cardiologists and people that kind of handle and place and insert pacemaker leads. So the body that just has wires running through it, right, or conductors running through it, to a surgeon is going to feel exactly like a pacemaker, just not be as long because, again, Paul mentioned we don't insert it quite as far. The chemistry that we place on top of those electrodes, so we're an electrochemical sensor, again, very similar to all commercial CGMs. They're all electrochemical sensors. They have some electrodes with chemistry on top of it that basically do the conversion of the glucose into some kind of signal. Very quickly, there's basically 3 generations that chemists refer to. Gen 1 is using glucose oxidase. And on the market right now, there are a couple of companies that have a commercialized Gen 1 chemistry. Gen 2 chemistry is where they shuttle that signal a little bit differently. Gen 3 chemistry has not yet been commercialized, right? It hasn't found its way into a commercial product. But to de-risk this system, we're using a version of what would be called Gen 1 chemistry. So we do have a glucose oxidase enzyme that's placed on top of those electrodes, protected with other polymers and membranes. And that's how the signal is generated.
So you're saying that this would last 3 years. The battery on my iPhone is much larger than this, and my battery doesn't even last a day. Like, how is something so small lasting 3 years?
Excellent question. And yes, and I struggle with the same, right? Well, fortunately is our device needs to do a lot less than an iPhone. We're not powering a screen. We're not streaming to cell towers, every so many milliseconds. So it's a lot less that it needs to do. So the power requirements are smaller. That being said, as I mentioned earlier, 2/3 of the entire device size is battery. We've designed the battery, or we've chosen the battery based upon the longevity of the chemistry, which is 3 years. If we push the chemistry out longer, we'll need a bit of a larger battery, or we can, migrate to a rechargeable battery. We considered a rechargeable battery, which would make the device dramatically smaller as well. But for our first generation product, we thought of 2 things. Number one, we want to keep it as simple as possible, both in terms of engineering and product design and manufacturing and all that. And secondly, for the patient, right? For the patient to have to recharge on a routine basis for a fixed amount of time. That's first we want to get the concept out, get the technology out, and if patients are interested in a much smaller device and are willing to recharge on a frequent basis, then that could be another generation of product.
Yeah, I'll just have like a little USB-C port on my chest that people can plug into.
One more way of kind of interestingly, I think a good way to portray it, in other words, is to think of it as our device is usually asleep, right? I mean, these types of devices that we're talking about, unlike your iPhone that I'm assuming you have on almost all the time, I don't even shut mine off when I recharge it, right? I mean, we should actually power cycle them a few times, but mine goes weeks without ever being shut off. Our device is awake for milliseconds, right? So But these are the kinds of design things. And by the way, here's ultimately the point I wanted to kind of bring up. We tried not to make these types of design decisions in a vacuum, right? We specifically went out and asked people with diabetes. We asked physicians, like we did market research and kind of stress testing these ideas of, if you had a device that was like this size versus this size, and we could give you 3 years with no recharging versus, maybe smaller but with recharging. So obviously little hassle factor. So some of these decisions were certainly focus grouped, if you will, right? And kind of thought of. These would certainly be the design aspects that we would continue to work on with respect to a pipeline, though.
Tell us about how, where it's implanted on the body.
Yeah, so the device goes, again, just like a cardiac pacemaker, Lita, it goes into the axial vein, which is, here sort of near the armpit area. And then it's advanced 2 inches or 5 centimeters into the subclavian vein. The axial vein merges with another vein, creates the subclavian effectively. And then it rests right there. So that the lead goes there. And then it is, sutured down and connected to the electronic device, which is placed pectorally under the skin.
So I wanted to, if I could add one little nuance, kind of interesting design aspect to that. Paul, by the way, for those that are listening only, right? He was pointing to his chest and he's pointing to his pectoral region, right? A little bit higher is your collarbone. We are contemplating a space that, again, is a protected space. So we're placing a sensor in an area that, you can roll over as you're sleeping and you're not going to go through a compression low, right, by crushing your collarbone. So there's some specific thoughtfulness, both again from kind of the surgical procedure and the familiarity with placing in this region and all of the procedural aspects of it, but also, to avoid kind of both motion artifacts, compression artifacts, right? This is a space for which within our anatomy is a thoughtful area, right, to go ahead and place the device.
And Mark touched on, he touched on two very good points, and I'll follow up on one of them, which is, we wanted this to be as close as possible to an existing procedure done by an existing skilled type of physician. In our case, the type, the physician who implants cardiac pacemakers. And, when that type of physician sees this, they have said, this is easy. This is a piece of cake. No special tools, no special training, no special equipment, no special lab. It's rather straightforward and simple for them. And so that should ameliorate or mitigate any concerns about rolling this out to a physician and then physician having to learn how to do it and doing the first 100 cases and that sort of thing that happens with new implantable technologies.
How invasive would this procedure be? What would it look like? Is it long? Is it a quick little thing?
It's about 20 minutes outpatient procedure in a cath lab. There's a local anesthesia to numb the area in the skin. So just, inject a little local anesthesia like lidocaine or something to that effect. And the lead goes in. Very, very, very simple, very straightforward.
How big would the incision be? Or like the scar? I'm thinking like a scar, right?
We're targeting it to be about a centimeter and a half type of maybe up to 2 centimeters. But no more than that. The device itself is less than a centimeter wide, but there is need to get access to suture down the lead, and so that might make it a bit larger. At the end, once it heals, it may be a little bit shorter than that because the edges don't usually show up.
Yeah, I know, Justin. You're gonna go ahead and post an image, but just as kind of a verbal visual. The device itself is narrower than a USB thumb drive and about as high. And it's kind of long and skinny. That's its aspect ratio. And that's purposeful so that incision site can be as narrow as possible, make a very small pocket, So it's lead first going in one direction and then device in the opposite direction. And then these two parts come together literally through an electrical connection and a set screw. So the surgeon just has a little teeny torque wrench. They hit that one set screw, tighten it down, slide the device into that small pocket, and then I believe bandage, surgical glue. I mean, we're also trying to be mindful, right, of not only that scar size, but how that wound would get closed up.
This device, you're aiming for it to last 3 years. Would you use the same scar incision just each time, you need a new one?
Yeah, you have a great set of questions, and you're you're thinking
I'm thinking about looks, right? Like right now, my
yeah.
CGMs don't leave scars, so I'm just that's something I would want to consider.
And you don't
I'd consider the pros and cons.
Right. No, exactly. And by the way, again, leveraging as much as we can with other techniques. That's already the technique. We'd call that scar tissue, actually, that we do want to form and kind of lock the device internally. I don't mean a scar on the exterior of the body, but the kind of that fibrotic capsule or fibrotic capsule that surrounds the device. You reuse that pocket typically with pacemakers, and the intention would be we would try to reuse that same pocket, right, for a replacement device.
And on the lead side, we've designed the lead so that the lead is actually replaceable to use the exact same vascular entry point. So
That's
you're
right.
not using up real estate of your vessel. It's the same point. So it will be replaced in the same spot.
So do you see this device for just all people with diabetes, or is there a specific cohort of people that this device would be for primarily?
Yeah, that's a good question. We get asked that a lot. So in short, obviously, all comers welcome, naturally. But primarily, obviously it's a medical device, so we're going to be limited to patients, who it would be a prescription indication. So patients with diabetes, in particular, we'll start off with patients who are insulin dependent. There's an argument to be made that patients who are type 2 who are not insulin dependent, that there's the set and forget aspect is very beneficial for them as well. But yeah, initial target population will be those who are insulin dependent, and we're trying not to segment further than that. And if you look at in the U.S. in particular at the number of patients who have reimbursement for CGM. The indications being, type 1, type 2, MDI, type 2 basal, type 2 hypoglycemic unaware, that's over 10 million patients. And yet, in the US who have coverage, and about half, a little over half, are CGM users. And so when you break down the reasons for why the other half is not using, there is a portion there that, we think we will capture. We think also based upon, all of this is based upon our market research. So we think there's a portion there we'll get. We think there's a portion of existing CGM users who, want to set it and forget it type of a solution. But, the bottom line is, do we expect to, capture 50% market share? No, that, we're wanting to offer, the market is large enough for multiple players, and we're wanting to offer a solution for patients who either can't or won't use the existing CGM, as well as those who are wanting to move on to something different for their lifestyle. So that's our target.
Today's episode is sponsored by T1D Exchange. You can directly make an impact on diabetes healthcare, treatments, and technology by participating in the T1D Exchange registry. It starts with a simple survey about your life with T1D, and it only takes about 15 minutes. After that, you'll have a personal portal with ongoing T1D study and survey opportunities. Plus, some of these studies even offer compensation. Signing up with the link in the show notes helps support my channel, and it allows me to continue putting out free content. You can sign up at t1dexchange.org/diabetic or click that link in today's show notes. Now, all this sounds good and dandy, but you know, that having a cool product and all that's one thing, but also the research behind it's much more important. So you completed your first in human study. Tell us about like what that consisted of, and then the findings that came out of that.
The objectives of that study. We tried to accomplish as much as we could, but make the study as short as possible to get as much information as soon as we could. So when you think of our device, there's really 5 things you have to prove: that the device is safe to implant, that it is safe while it's implanted, it functions while it's there, it's safe to remove, but while it's there and functioning, that it lasts as long as 3 years. In our case, we want to target 3 years. So we can get 4 of those 5 with a short-term study. So we did a short, 4 to 5 day, depending on the patient, 4 to 5 day study, and we did a handful of patients, 2 handfuls of patients, to look at those 4 factors. We did it outside the U.S. We did it in Sao Paulo, Brazil, at a very prestigious cardiovascular center. Why did we choose a cardiovascular center? Because we needed that skill set for the implantation of the device. Obviously, we didn't create any scarring. Again, the idea was to assess the procedure and its functionality and its safety and so forth. So we put the lead into the vessel and had it come out percutaneously. So the lead just went in through a needle type of an approach, right? And an introducer, so there's no scar. And it came out to external prototype electronics that were taped onto the body. And the patients were kept in hospital for several days and monitored, just to make sure that, there's no safety issues. We didn't expect safety issues, especially based upon how much of the technology from the cardiac world, cardiac pacing world in particular, that we've leveraged. And they don't have these massive issues. Maybe in the 80s they had some of them, but not today. So we wanted, there's still some folks who, oh my gosh, you're sticking this in a vessel, aren't you going to cause this problem or that problem? We wanted to get also very good, early, quick, safe data that shows that no, these are not concerns. You don't have to worry about these problems happening within 48 hours and that type of a thing. So those were the objectives of the study, and we proved, we were able to meet all of those objectives, that it was safe it was safe to get in while it's in, safe to remove, it functioned while it was in, and we had also, good performance while it was in. We wish we had better performance, and we will get there on our next study, and but we're very happy with what we had achieved.
So you were getting readings from it. It was
yes.
functioning. Yeah.
Yes.
And that's what you said. And then, and the results, you were happy with the results, but you can do better.
Exactly. And okay. Some of the difficulties that we had was because we were bringing it out and connecting to external electronics and taping to the body, and some of that stuff, introduced, some noise, if you will, that impacted the accuracy. But as I said earlier on the call, that, still overall our numbers are lower than, what's commercially on the market. Now, that being said, the patients and the physicians were blinded to the data. This is a retrospective analysis. It wasn't a real time, forward-looking analysis. So I want to be transparent on that. Yeah. And we do know that, that does add complexity and does add more noise to the equation based upon, the algorithms that are needed to calibrate the device.
Yeah. And I do have images of the device that you use, the one with the external electronics, which I'll put on, which will have been on screen already for people watching, or it's on YouTube. And now, what is the next step for your development and research? You did the sheep, you did the first in human. Is there now like a longer term study that needs to happen? Because that was just a few days, right? This first in human one, it was very short term.
Exactly. Yes, indeed. So now that we're comfortable and we think, ethics committees and so forth will be comfortable that, everything is as safe as we believed it would be and is functional. So we're ready to do a long-term study. We're in the process of getting ethics committee approval in Australia to do a multi-center study there, 2 centers up to 30 patients. And this will be for the fully implanted device. And as of right now, it's designed as a 1-year study, not because we think the chemistry is going to die in 1 year, but because it's tough to recruit a patient for 3 years, and understandably. So things will keep running after a year. We'll figure out with the patients and the investigator and the ethics committee what we're allowed to do thereafter. But yeah, that's set up. We're hoping to have our first patients. We'll get approval literally any week now, and then have our patients. The first patients implanted in late June, early July. And in parallel to that, we've also done a pre-submission to the FDA to start that process to get what we call a U.S. pilot study, which will be, if all goes well with the Australian study, this will be a rinse and repeat of that study. It'll be 3 centers as opposed to 2, all in the U.S. It'll be 40 patients as opposed to 30, of course, pending FDA's approval to all of these design requests. And similarly, it will run for a year, maybe more, depending. And that is intended to be, and we are hoping we will get approval by the end of the year and start early next year. Oh, then lastly, that is intended to be a dry run for our pivotal trial, which is the trial for commercial approval. And so that one we anticipate starting, sometime around, if all goes well, later 2026.
Amazing. For a second, I was like, oh, well, I guess I'll have to move to Australia. But knowing that there's a trial coming to the US, maybe I won't, maybe I can
maybe not
be part of it. We'll see.
Yeah, that'd be great.
That's awesome. So it sounds like it is, you're very much in development. There's a lot of great stuff coming up, but this isn't happening in a year, right? Like there needs to be at least a year of these trials, and then the US one's going to happen maybe a little later. So this is like, could we see this, and is this like a 3 to 5 years kind of thing if all goes well?
Yeah, if all goes well, our target is, commercial approval in, the second half of 2028. So, a little over 3 years, if all goes well. Wow. There's a lot that, obviously we need to make sure that we're working, of course, and all the devices were functioning and so forth. And we're pretty confident in that, but you never know what you don't know until you do it. And then, of course, there's also, working with the FDA. They've been, by the way, they've been phenomenal. They really have. You can't give, in its early stages, but I mean, they've been so responsive so early. It's really hats off to them. And so, but that being said, they have to protect, the customer, the citizens, right? They have to protect, people from, and so they're going to have their requirements, and they may want us to go slower or do certain other things. We'll find out. But they have been very good to work with thus far.
Very cool. Glucotrack recently announced participation in the European Forget Diabetes Initiative, which is aimed at creating a fully automated pancreas technologically. Tell me a little bit about that partnership and why you joined it.
They had reached out to us. So that project has been going on for a few years, and so it's they reached out to us. They were looking for an implantable glucose sensor to be part of that program. I can't speak to what happened in the beginning parts of the program because I wasn't there, but that's why they reached out to us and came to us, and we would absolutely enjoy to be part of that. It took quite some time, to get everything through, the regulators, and especially since we're not a European company. But we actually just this week did our first implants in preparation for that particular study with the pump. The first implants are, of course, without the pump. As Mark mentioned, we've been using a sheep model, and for the reasons that he cited. But this particular study will be using the porcine or the pig model. And so we're just getting our teeth cut on that pig model this week. Our first a few pigs are being implanted this week, yesterday and today, actually. So it's happening. We're excited. We are interested because their pump is actually an intraperitoneal pump. So if you reflect back to earlier part of our conversation, there's these 2 compartmental delays, right? Glucose and insulin. Well, this would be the compartmental delay for insulin in the intraperitoneal space is much, much lower. And as Medtronic proved with their implantable insulin pump many years ago. So, yeah.
Yeah, the people using the implanted insulin pump absolutely love it. Like there's no such thing as a pre-bolus. It's a bolus and you have to eat right away because it's going to work in that intraperitoneal space. It's going to activate. There's no, fat in the way. So, wow, I didn't know that they were working also with an implantable pump. So that'll be really fun to follow. Thank you both so much for coming on the show. This was such an interesting conversation. I'm really hopeful that a device like this will be around by 2028. I mean, I can easily see how it could help me out with my treatment. And, if a cure is not going to come, then a technological cure, this, fully automated pancreas that's inside me, or at least half the equation with the CGM would just be wonderful. So, I wish you the best with your work on this. And I hope that it all works out and that I could be the first to use it.
We'd love to have you there. Yeah. Thank you, Justin. I really appreciate your questions. Very thoughtful, and we look forward to continuing to share the journey with you.
What do you think about this technology? Let me know in the comments, and make sure you subscribe if you're on YouTube. And if you want to watch these in video, you should watch them on YouTube. We show a lot of great resources along with the conversation. And we've got our blog and newsletter, diabetech.info. New articles are going up every week. A link to that is in the show notes. You can also sign up for our bi-monthly newsletter with all the updates in diabetes tech and research and our content. Other than that, I'm Justin, and I'll see you next week.